So class is recording, and I took a small data set and I looked into, I was actually trying to understand whether the data is linearly related or not. Okay? So basically every algorithm will have its own assumptions, and linear regression has got 5 assumptions. We are actually clearly looking into these 5 assumptions because linear regression algorithm is used for inferential purposes, whether the data is linearly related to the target variable or not. Okay, so linearity is one assumption. If data is linearly related to target variable, then the algorithm will give you higher accuracy. Okay, so to test that, we can use either two graphs are there, observed versus predicted plot or predicted versus residual plot. To explain that concept, I've taken a nonlinear data set here. I've taken a nonlinear data set here. Right? This is the nonlinear data set. There is one input variable, one output variable, and then the data is related like this. These blue dots are the data points. Right? For each x, there is a y, x and y, x and y. I'm actually dotting, and then I have got a nonlinear data set, and I fitted a linear regression model. When you use a linear regression model, it's always going to do a straight line, right, through the data. So it did a straight line, and then I looked into the errors and the predicted values, and the predicted values and errors graph is actually coming with the, resembling the same pattern as the original data pattern. So why we are actually looking at this is, when you have one input variable and one output variable, you can do a two-dimensional plot and understand whether data is linearly related or not. Right? In this case, it is non-linear. So you can choose the appropriate algorithm and fit the data in such a way that a line is drawn like that. Okay. If there are more than one input variables, right? If there are more than one input variable, you will not be able to do this graph. Do you agree? You will not be able to do this graph. Do you agree with my statement? When there are more than one input variable and one output variable, will you be able to do this graph?
No.
No, right? So how do you understand then? When you are unable to do this plot, you will not be able to understand how data is related, how all input variables are related to output variable. You don't know. You don't know how, which algorithm fits, right? You need to fit linear regression algorithm, see the accuracy, other algorithm, see the accuracy, like that. So to understand the visually how the data is related, you can use this plot. Whether there are n number of input variables and one output variable, or one input variable and one output variable, you will have only one prediction. Right? There are n number of columns, x1, x2, and so on, xn input variables, and one output variable y. Okay, and you are actually trying to do this plot. You will not be able to do this plot, but you can make prediction, and the predicted column is going to be one column, and you can calculate error. So when you look at prediction and error, do a plot, it is actually resembling your original data. Your prediction and residual plot is actually resembling your original input and output data. So by looking at this graph, you can understand the data pattern. So the conclusion is that whenever you get a regression data set, you first build linear regression algorithm and then do predicted versus residuals plot. Look at the pattern and appropriately choose the algorithm. Got it? So linear regression algorithm is useful in making inferences or in understanding data and choosing the algorithm. Do you got it? Any questions? Do you get it? Okay, so I think you are good. So predicted versus residual plot is that one. Now, when algorithm is not working well, right, you may have to apply the transformations on input variable. When the, especially data is non-linear, you need to apply non-linear transformations on input variable. This is called as polynomial regression also. We'll talk about that in coming classes. So in our data, in our Now the salary data, when I tried to do a plot, I found some outliers here. Right? Outlier analysis also you can do using linear regression algorithm. You can do outlier analysis also. If the model is fitting well, the observed versus predicted graph should actually fall on the line, on this 45-degree line. No, the observed value and the predicted value are same, right? Then what happens? Everything will come 1 1 2 2 3 3 4 4, like that it will come, right? So it will fall on that line. Rather, right, it will not fall. It will actually go the other way. Far from this red line. So I took some threshold there, right? While doing this plot, I took some threshold there and then plotted, right? I plotted plt.txt and data point, and then I plotted the index there. Now, if the error is greater than 5,000 rupees, then I plotted the numbers also. So we know the outliers also in this data. Okay. So residual source versus fitted plot, when I looked into it, right? It's actually. Do you think the data is linearly related? Do you think the data is linearly related or not? Is there a non-linear pattern, linear relation, or no pattern at all?
To some extent, it's looking like a linear relationship.
Yeah, to some extent, it is looking like linear relationship. How did you say that? When I look at that graph, right? This red line is here, and all dots are like this dot, these dots are actually far. It looks like far. Still, even I think the same. What you think? Like it looks like there is some linear relationship. How can we say? Why it is actually looking far? Understanding graphs.
Standard deviation 0, the density
Yes,
is more,
yes.
or
Yes,
close to
yes.
standard density is
Yes,
more.
yes.
That's why we can think that it's close to linear.
Very good, sir. Very good. So whether you are getting the concepts or not, I'm actually I'm trying to understand graph here. So I standardized the error and the predicted values. If you look at the error, right, within one standard deviation, most of the data is there. See that? Maybe I should give me 1 second. Okay. Let me. That point is very correct, Girikaru, whatever he said, very correct. So within one standard deviation, there is most of the data. Right? Within one standard deviation, there is most of the data. Within two standard deviations, right? Some data is within three standard deviations, most of the data, 99.3% data actually fall within three standard deviations. Error, right? 99.3%. So we're going to talk about this. Data is actually linear. So if you don't standardize the data, right, you will not understand. If you don't standardize the data, there will be numbers here, and here also there will be numbers. You don't know whether it may look dense, it may look thin, right? The dots may look dense, or dots may look thin, but you don't know what's happening. To get clear picture, you should do normalization of the data, and then only you should do the predicted versus residual plot. Got it? Any questions there? Good. So the next point is heteroskedasticity should not be there in the data. Homodescarticity should be there. Okay. So what is homodescarticity? If you have one input variable and one output variable, and if the data is like this, right? If data is like this, all data is close to, for a given x, there are different y's, right? If you look at this, why these dots are actually coming, one bottom, one up, and like that. For same given x, there is some y, there is some y, right? There is some y here, some y here. But those y's are actually close to each other. If you look at whole data, any place, if you look at a given x, there will be different y's, but they are close to each other. That is called as homoskedasticity. If homoskedasticity is there, then the linear regression algorithm will work well. Okay. So this is called as heterodescarcity. Heterodescarcity should not be there. When you have heterodescarcity, your plot will look like a funnel. See this? It looks like funnel, right? Right? Funnel means that in our childhood, a kirana shop they used to use it, right? So this is the funnel, right? So this funnel shape, why did it came? Can anybody explain why this funnel shape came? Can anybody explain why the funnel shape came there?
See, when we increase the x, there is lots of deviation from predicted value.
We should not be saying increase the x for the axis when they are growing, or the funnel can be opposite direction also. In the data set, funnel can be opposite direction also. The tilted.
Rightly skewed.
No, not rightly.
Right skewed to data.
No, when you say skewness, right, it is about one column. It is not about two columns, right? Skewness is all about one column. Do you agree? Yes, no?
Yeah.
No?
Right.
Skewness and kurtosis and normal distribution are about one column, one feature. That's the clarity we should get. Okay, this is about two column bivariate analysis. This funnel can be in the opposite direction also. Let me try to explain that. Why this is not going up? So let me take a screenshot. So if this funnel is in the opposite direction, right, like this, and then your fitted model, right, fitted line is like that. What do you say then? This is also heteroskedasticity only. Okay, but it is in opposite direction. When x is minimal, there is variation, lots of variation in y. When there is y is maximal, variation is less. The term is also very right. The variation is less, right? So for given x here, there are different y's, and they are very far from each other. Okay, I took the example of Mumbai. There will be slum, next to it there will be big high-raised buildings. The high-raised buildings, the same location, same locality, the slum area prices are these, high-raised building prices are these, and maybe mid-level apartment prices are these, like that, right? If your data is like that, right, so in some areas it is okay, the variation in y is not that much, right? In some areas the variation is actually growing, and it actually became like this. If your x and y are related like this, the heteroskedasticity may happen. How to find out when there are more x's? If I have only one x and one y in the data set, only location and the price, I can do a graph between x and y. But if I don't have, if I have more than one x, x1, x2, and so on, xn and y, this is the data set. I have got, number of bedrooms, number of bathrooms, and all that data is there. How can I find whether heteroskedasticity is there or homoskedasticity is there? Guys,
Predicted versus we need to make a prediction.
good sir,
from
good,
all the
very good.
input.
Right? Predicted versus residual plot will actually resemble your original data's pattern. So you need to do residuals versus predicted plot, and it will show you. If the residuals versus predicted plot is showing a funnel shape, then you should be saying the data is having heterodescarcity, right? Heterodescarcity, right? So how to do that? You actually predict. You fit a linear regression algorithm. Only linear regression algorithm will give you this clarity. Other algorithms will not give you. Predict y cap, predict error, and then do a graph between these two columns. If that is like this, then your model is good, right? Anyway, if it is like this, right? Anyway, you will get high accuracy, right? High R square score. But if it is not, giving a high accuracy score, then you should be looking at the predicted versus residual plot. If the plot is like this, then there is a heteroskedasticity. What is the solution? We said that when y is growing, right, as our sorry, when x is growing, y is actually deviating a lot, or y violating a lot. If you look at only y, then then what's happening? I think if you look at only y and try to do a plot, right? When it may be, yeah. I think Sesiram, whatever you said is right. If you only look at y, it may be left skewed or right skewed, either this way or this way. Got it? Got it? Too many low values or too many high values. Sorry, this is too many, yeah, low values and too many high values. Did you get it? Did you get the clarity? Your past statements are also right. When y is right skewed or left skewed, then there is a possibility of getting. There is a possibility. It is not that guaranteed. Right? If x is also actually oscillating like that, right? Then there will not be a problem. X is also right skewed or x is also left skewed. There will not be problem. Only y is right skewed or left skewed. Then you may get the heteroskedasticity. Did you get it, guys?
Yeah. Okay.
Thinking along, right? You need to think along. Whatever. I am actually somewhere in my mind. You should be there. Any questions? Clarity needed? Good. Okay. So how can we fix this right skewness or left skewness? Can we apply some transformation and fix it? If we fix this, can we make this this high variance into low? Can we shrink these
Apply
values? Log transformation, right? If you apply log transformation, these big numbers will become small. These small numbers will become a little smaller. So then what will happen is the graph may come like that. Okay, and then you fit a straight line, it will be able to predict the values well. So now, right, to fix a heteroskedasticity, what we did, we actually applied log transformation on y value. If you make a prediction using the data, using input, will you get log y or y as the predicted value?
Log y only.
Log y, right? Are you guys getting it? Rest of the people, don't hesitate.
Yes.
Right?
Yes.
So you actually, what I said is, if you find heteroskedasticity, how will you find heteroskedasticity? You take the data, you build a model, you build a linear regression model, and then try to do a residuals versus predicted plot. If you are getting a the funnel shape diagram like this, then you have heteroskedasticity in the data. So if you have heteroskedasticity, you need to apply log transformation to y. Why do you need to apply log transformation to y? You need to shrink these values. If you shrink these values, right, if you apply the y values, bigger y values become small, smaller y values become even a little small. Give me 1 second, I will be back. Oh, sorry for that. So when you apply, log transformation to y, you are actually trying to predict. When you predict, right, you get log y. I think I showed you this example before. Let me show you that. On the website we had a blog and I explained that project, right? So complete end-to-end project execution. In that we have this. We actually were able to find. Generally, data sets will not show you the heteroskedasticity behavior. This is from GitHub. It will take some time to load. I think. So here, when I built a model, I got only 48% accuracy. Okay. We got only 48% accuracy. Then what I did, I already built a linear regression model, right? I did a predicted versus residuals plot. See this? Do you see a funnel shape here? Do you see a funnel shape?
Yes.
Right? So we
Yes.
applied, yeah, that's where we applied log transformation. Right? Then I built a model. Right? Now the funnel shape is gone. Right? But still the model is giving only 57% accuracy. That means there are other problems also. But in reality, if in reality, are like if the model had given 90% accuracy, right, I would have used this model, right? When I predicted, I would have got log value of original y, original y. So I need to apply reverse transformation to find out the original y or the predicted y. Okay, so that's the point I wanted to explain. So now you look at this code, you'll understand better. We have covered all the inferential statistics and all the concepts. You look into this code, you'll understand it better. Okay, that's an exercise. You definitely need to look into this code and understand, if possible, the data set is there on the internet. Melbourne data set you call it as. I think I kept it in the data sets also. If you say at Kaggle, from Kaggle you can download that. Okay, and then you yourself try to do some experimentation. What I did may not be right. So this is a good exercise. This is a very good exercise, and you start doing it this Saturday. You all should be showing something to the Keshava or Balabhaskar. Okay, will you show? Will you work on this?
Yeah, sure, sir.
Yeah, please,
Yes. Yes.
because if you work on this, right, you will get more clarity and you will be able to think along, right? Think along is what is needed. I will be somewhere else and you will be somewhere else. It's not going to work out. Our mind should be at one place. Okay. So this is heteroskedasticity. To understand heteroskedasticity, to understand whether to apply a transformation on X or a transformation on Y, you should know what is predicted versus residuals plot and how it actually works. Okay, that's where I took this much time. This is not about linear regression or linear regression assumptions. This is about why the algorithm is not working. When I fitted a linear regression algorithm, why it is not working, or how to choose the best algorithm. We'll know different algorithms in coming classes, but when you know about chisel, you know about axe, you know about dagger, you know about everything. But when to use what, which fits what, you need to know. That's the problem I am trying to solve here. Okay. The next thing is normal distribution of error term. So just now I actually pointed that out. If you look at this, error terms, right? Predicted versus error graph, right? it looks like normal distribution. Most of the data is within one standard deviation. Okay, and a little data is actually falling between 1 and 2 and -1 and -2, and between -3, and beyond is like less data. So it is almost normally distributed. When the error term is normally distributed, that means your data is linearly related. It's a simple concept actually. Right? The simple concept. If you understand it in a reverse way, in an opposite direction, and if your data is linearly related, right? I have x1, x2, and so on xn number of features, and then there is y. I fitted a linear regression model. I predicted y cap, right? I predicted y cap. Now I found out y minus y cap, that is error. And to this column, right? To this column, I am actually doing a plot. I took this column and doing a plot. When I do a plot, if this is a real number, should I be doing a histogram or a bar graph? Should I be doing a histogram or bar graph? Should I be doing a histogram or bar graph to error term?
Histogram.
Histogram, single column.
Yeah, histogram, right? So it's a single column and a numerical, right? It's a numerical column. So I will be doing histogram. So if I do histogram, what is an x-axis? What is an x-axis? I am trying
Minus
to.
y bar.
Yes, y minus y bar.
Predicted value.
Yeah. No, error.
Yeah, error. Sorry.
Error.
Predicted.
So error is going to be on x-axis, and what is on y-axis? If I am doing histogram.
Counts.
Yes, right. So we are trying to check whether this particular column is normally distributed or not. To do that, you do that, right? You take error term and then count on y-axis. You will, if you are getting a like that, right? Then the errors are like that. Bars are like that. So errors are normally distributed. What is errors are normally distributed, and what could be the value here? What could be the value of x here? I will take what could be the value here?
Value of x, sir?
Value of x and
So that is nothing but error equal to 0.
Yes, very good, sir. Very good. Right? Error 0. Right? Most of the errors are close to 0. When that will happen? When that will happen? All the x's are linearly related to y. Your y cap is actually close to y. Right? Your y and y cap are close to y, close to each other. You will get 0. Right? A numbers close, numbers very close to 0. So if your error term is normally distributed, that means there is linear relationship between input and output, and there will be a 0 here, and most of the data, 68% of the data within one standard deviation, 95% of the data is going to be within two standard deviation, 99.7% of the errors, 99.7% of the errors are going to be within 3 standard deviations. Okay, normal distribution is the only one thing you need to understand from statistics, but we covered all that because you have to have that knowledge, right? That whole feel of statistics. So to give you a feel of statistics, right, we understood all that. So here, if your error terms are distributed normally, we are saying there is a linear relationship, or the linear regression algorithm will work. One of the assumptions of linear regression algorithm is that error terms should be normally distributed. When you fit a linear regression algorithm and look at the plot, look at this normal distribution plot of the error term. If it is normally distributed, you are good. Okay, the model is working good. Our linear regression algorithm is very fitted for the data we are trying to build a model. Okay, that is the third assumption. A normal distribution of error terms should be there. Okay, calculation of confidence interval and various significance tests for coefficients are all based on the assumption of normal distribution. So the coefficients confidence interval we have seen, right? This confidence interval. Right? If error term is normally distributed, right, you can take them as taken for granted. Okay, if the error term is not normally distributed, even though the confidence interval is low, right, 95% confidence interval range is low, you cannot take it for granted. So, this normal distribution is, so the error term is not normally distributed. It's a kind of red flag that the particular algorithm, this linear regression algorithm, is not going to work on the data set. Okay, it actually clearly says. So when we looked into the bar graph or histogram, right, we were actually worried about how to choose bins. Do you remember? Do you remember that? I don't know. Let me show you that. Which class it is? Yeah, salaries, right? Salaries data I showed. Which class it is? It was data distributions, I think. Yeah, see this here? When I actually chose the bins, different bins, bin size, right? I had got a different kind of a plot here. Do you remember that? Do you remember that? See this here? If I don't choose bins, even though data is normally distributed, it is showing that it is not, right? Right? So you need to carefully choose bins to in a bar graph or histogram when you are trying to understand a particular column's distribution, right, pattern of the distribution. You should actually choose the bins carefully. If you don't choose bins carefully, you will not understand. Even though the data is normally distributed, it will not show. To solve this problem, right, there is a plot called QQ plot. If you do QQ plot, right, definitely it will show. If you do a QQ plot and all the data points are actually close to this red line, that means data is normally distributed. Whether, irrespective of, the histogram is showing clearly the normal distribution, no need to worry about the bins. So you need to do QQ plot. What is QQ plot? If the distribution is normal, the QQ plot, I'll explain what is QQ plot, but first I'm trying to explain what it is actually explaining. When you look at QQ plot, right, what you will get out of it. The points on QQ plot should fall close to the diagonal reference line. Okay, the bowl-shaped pattern of deviations from the diagonal indicates that the residuals have excessive skewness. S-shape shows that excessive kurtosis. Okay, sometimes the problem is revealed to be that there is a few data points both times. Outliers are there. Okay, so you can use statistical tests are also there. We will get this Jarkberry test here, and which should yeah, this test. I think this value should fall in some range. I forgot the range, but not needed. No, this is not that important. So there are tests also to find out whether data is normally distributed or not. Kolmogorov and Shapier-Wilk test, I think I was actually showing before. Shapier-Wilk test, I'll talk about it in a moment. Okay, there are some statistical tests also with which you can actually understand whether data given column is normally distributed or not. Okay, so here we are looking at QQ plot. If the plot is actually like this, that means data is the error term is normally any column is normally distributed. If it is forming a bow shape, right, like this or like that bow shape, one direction is left skewed and another direction is right skewed. And if it is forming S shape, right, like that, right, S shape, and then it is a kurtosis. Lots of kurtosis is there. Right? Kurtosis is good in a way, right? Most of the data is actually falling in close to the. If it is zero, the mean is zero, then it is good. If mean is not zero, then maybe model is actually trying to predict all values a little far from actual y. Okay, what QQ plot is doing? How actually we did this plot? Okay, do you have a question on this? When you look at this QQ plot, I'm actually putting dots, but I passed only one column here, right? SM, right? Stats models dot API QQ plot. I passed only one column, residuals. Do you agree? This is one column or two columns? Is this one column or two columns?
One
Right.
column, sir.
Right, it is one column, and I'm actually showing you dots, right? Can we do one? Can we do a scatter chart with one column? That's the first question. Can you do a scatter chart with one column?
No.
No, actually.
Then why did we got? How did we got two, right? Dot here. That's the
Yeah,
that's.
Maybe it is actually calculating internally.
It is calculating internally, right? What is it calculating? I'll explain here. See this here, theoretical quantiles and sample quantiles. Okay, theoretical quantiles we need to understand. What we know, let me, I think, yeah. So, what theoretical quantiles is, normally distributed data we can generate. Do you agree? We can generate normally distributed data, right? Do you agree? Can you generate normally distributed data? Can you tell me one example of a column? Some column X1. Can you tell me a normally distributed data in X1 column?
You say 1, 2, 3, 4, 5, 6.
May not be. 1, 2, 2, 3, 3, 3, 4, 4, 5, right?
Okay.
5, 5,
Fibonacci is something.
right? Sorry.
Yeah.
Right? Now if you do plot, right? Now once there is only one, there is only one, right? Twos, there are two twos, right? Threes, there are three threes. Four, there are only two fours. Fives, only one five, right? This is normally distributed data. We generated it, right? So theoretical quantiles means it will generate data between around zero. It will generate data around zero, which is normally distributed. Okay. How many numbers it will generate? Our data set has got 32 records. Okay. There will be 32 errors. Right. It is going to generate normally distributed data, 32 numbers, which will have 0 as mean, 0.0 as mean, or it will take 0 as the center and generate 32 numbers. Now, what it will do is, it will do a plot between generated theoretically distributed, theoretical quantiles, generated normal distribution of normally distributed data and our data. What is our data? Errors. Okay. If they are actually forming, if they are actually forming a straight line, the angle may not be that important. If they are forming a straight line, that means our data is normally distributed. If not, our data is not normally distributed. How? How is it working? If you take a simple example here, I'll generally take this one, x1 and y, 1, 1, 2, 2, 3, 3. If you take and try to do a plot, what will happen? You'll get a straight line, right? Right? Suppose that you have another data set like this. There is 1, 10, 2, 2, 3, maybe 15. Or I cannot, maybe, 1, 3, 2, 5, or maybe 3, 1. If the data is like this, right, what will happen? What will happen to the graph? 1, 3 will actually be somewhere here. Now 2, 5 is going to be somewhere there, and 3, 1 is going to be somewhere here, right? And now the graph will become like that. Why this became like this? Now why this actually formed a straight line, and why this formed a curvy line? What's the reason? Is it because of x1 or y? I plotted two graphs here.
Why?
Huh?
Why?
Because of y it actually, right? So this is the analogy there, right? You take normally distributed data, theoretically normally distributed data, one column, and your data, right? Try to do a plot. If this is actually getting distracted, it will be because of this your data. It is not because of theoretical data. Because theoretical data is perfectly normally distributed, right? If it is coming proper, it is because of your data, right? Properly getting the graph, or the dots are forming a straight line or not forming a straight line is all dependent on your data. If your data is normally distributed, it will form a straight line. If your data is not normally distributed, it will not form straight line. Did you get it? Any questions?
So that means like theoretical quantity always same for any data set.
Yes.
Means like any
Yeah, any data set. It actually takes the number of how many number of numbers it should generate.
Okay.
Got it? So they are, very interesting concepts. These are, very simple, and I actually, I kind of enjoy these concepts. Very simple, right? If you look at this, right, carefully, if you look at, at a high level, right, this is theoretically normally distributed data. Okay, and this is your data. Error, right? Maybe it is like that, maybe a little like you cannot actually get exactly perfectly normal distributed. So what it will do is this dot is going to be from here. Now x will be taken, sorry, x will be taken from here. This is theoretical normal distribution. Y will be taken from here. This dot is plotted. X will be taken from here. Y will be taken from here. Another dot. X will be taken from here. Y will be taken from here. Another dot. X will be taken from here, Y will be taken like that. These are called as quantiles. Interquartile range, we have 3 quartiles only, right? 3 quantiles only. Here we'll have n number of quantiles. 32 records, 32 quantiles it will take. For every data point in your error term, it will actually choose corresponding data point from the theoretical quantiles. It will actually choose appropriate in parallel number it will take and try to do the quantile to quantile plot. Now, right, you understood what is quantile to quantile plot, but the point you need to remember is it should form a straight line. These dots should form a straight line. If they are not forming a straight line, or if they are forming a bowl shape, either upward, concave or convex bowl, that's a skewness is there in the error term. And if it is forming a S shape, there's a kurtosis is there. If S shape kurtosis, if the center number is 0, then it is good, because most of the errors are coming close. So generally normal distribution is what is expected. Then the algorithm expects normal distribution. The error term is normally distributed. The data set is linearly related. The input variables are linearly related to output variables. If not, whatever problem you can understand, and you may get a clear, clarity, a little bit of clarity on which algorithm to use and things like that. Got it?
Sir, one question, sir. There.
Yeah.
On the x-axis, is it standard deviation of residual? Is that what it is?
No. Theoretically generated data around 0. Theoretically normally distributed data Generated data, it is around 0. It is generated 0 data. You can generate normally distributed data using np.random.rand method.
Yeah, that is correct. That is for what? That is for residual values.
No.
Because we input as residuals.
Sir, it is a simple. No. Let me explain it in a general terms. Suppose that the y-axis is a current politician. X-axis is Rama. From the mythology, our god Rama. Okay, we don't know whether he was there or not. We know that he is there, but many theories say he was there or not. You can take the personality as theoretical personality, and then our current politician as the real personality, and then compare. You will understand how the current politicians are actually working, right? The same way, we are actually generating some numbers and trying to compare it with our original numbers, original errors. Got it or still not here?
Okay. Can you tell me what is the y-axis, sir?
Y-axis is your errors.
Okay, error value.
Error values. 32 errors are there. You are going to generate 32 numbers which are normally distributed, and you are going to do plots.
Okay.
You're going to do dots there.
Sure.
Right? Clear, right?
Yeah, in the previous. Okay, go ahead.
I closed it.
Yeah, no. Just theoretically also we can imagine.
Please go ahead. Explain it.
Yeah, once you just now you have derived a normal distribution stuff like 1 1 2 2
like that.
So
like that.
Here, so we are taking 32 numbers and trying to generate the normal distribution because
Yes.
our count of data is 32.
Yes.
Okay, but the y-axis is showing us the scale is something like minus 1.5 to 1.5.
That's okay. Doesn't matter if it is minus 1.5 or 1500. It doesn't 15,000. It doesn't matter.
No, I think x-axis the for theoretical standard deviation numbers they are correct, sir.
Normally distributed data.
Correct. For normally distributed data, these are the standard deviation numbers. That's what
it doesn't matter, sir. It doesn't matter. We are generating numbers between minus 1.5 to 1.5. You can generate numbers between 15,000 to 15,000 also. It doesn't matter.
Okay, now. Yes.
If you generate, let me tell one point. Here on y-axis, the range is between minus 10,000 to 10,000, right? If your generated data is also between minus 10,000 to 10,000, then you will get a straight line which is around 45 degrees. If not, the angle will change. That's it. You're asking something.
Yeah, okay. So this range is decided by the QQ plot internally?
Yeah, QQ plot will take it internally.
Is it based on, it's based on the sample quartiles, right?
No,
it's based on the residual. It's based on the input data. It's actually deciding the range and then
number of numbers it is deciding. How many numbers it should count? How many count it will take? How many numbers it should generate is taken from your error term, count of error terms. That's it.
But the range could also be something different, right? Why it is taking only minus 1.5?
Why are you worried about the range? Why are you worried about the range? That let us understand that. If you understand that,
actually frame my question differently. So is it always be minus 1.5 to 1.5?
I never observed it, but if the number of numbers increase, right, the range may also increase sometimes. I never observed.
That's what if this is static like minus 1.2 to 1.5, I won't be worried. But if it is changing, why it is changing and how it is changing is a concern, right?
However, it is changing. The concept is that you are actually comparing your data with completely normally distributed data, right? Why
Yeah,
are you
I
worried?
got it.
You no need to be worried about that. That's the point I am trying to explain. That range doesn't matter for you. It is just that you are trying to compare your data with ideally normally distributed data. That's it. If you get a straight line, your problem is solved. Whether data is normally distributed or not, that's your worry. That's it. QQ plot is giving you. The basic idea is that comparing your data with normally distributed data. How much range, it doesn't matter. If the range is actually with the, if the range is like this, you will get a line which is around 45 degrees. If the range is not like this, you will get a slightly tilted line. That's it. It's a line angle will be like 30 degrees or maybe 20 degrees or maybe 10 degrees or 0 degrees. It doesn't matter. Got it?
Yeah, yes, sir.
Got it, right? You think about it, you think about it and not needed. Range we are not worried about. We know how it works, how to use the tool. You need to understand. And anyway, we understood already. I think I am actually talking about it, but I'm not clearly saying that the range is going to be fixed because I never looked into that point because it doesn't matter to me. If the range is too small, the angle will actually go even down and down, right? Now the range is same, then it will be 45 degrees. Right? 1, 2, 2, 3, 3 is the data. And you do a graph, it's going to be a 45 degree line, right? Going diagonally, diagonally, it goes like that. If it is, 1 minus 1, 2 minus 2, 3 minus 3, the angle is going to be different. That's it, right? Got it?
Yeah, if the angle is 45 degrees nearer to 45, so this data is linearly associated.
No. The data should be linear. That's it. It should be close to that red line. Angle doesn't matter.
Okay.
Angle doesn't matter. If you read through this content and look at the graph and maybe watch that 5-10 minutes what I explained there, you'll get more clarity. If you still have questions, right, tomorrow we'll discuss. Is that okay?
Yep, that works. Thank you.
So, histogram I did, and I don't know whether it is normally distributed or not. QQ plot is more clear. You can use QQ plot to understand whether it is normal or not. Okay. Violation of normality in the errors can be fixed by, the distribution of dependent and independent variables are non-normal. This is one reason. Right? This doesn't mean that you convert all the input and output variables to normal distribution. It will give you the linear regression algorithm will work. Okay, the statement clearly listen to this. When the input variables and output variables independently they are not normally distributed, error term may not be normally distributed, but vice versa is not true. If you try to convert if you apply transformations onto x and y so that you make the data normally distributed and then build a linear regression algorithm, it is not guaranteed that you get a normally distributed error term. Did you get it? Vice versa is not true. One direction is true. If your x and y are normally distributed, your error term may be normally distributed. Okay, provided the data is linearly related. Okay, if you built a model, you are not getting a normally distributed error term, you try to convert or apply transformations onto your input data and output data so that you convert them into normal distribution and build a linear regression model, it is not guaranteed. Okay, so the linear assumption is violated. The basic problem is linear relationship is not there between the input and output. That's where your error term is not going to be normally distributed. But here, fortunately, we got the error term as a normal distributed error term. Okay. Any questions here on this? At this point?
Sir, the reason why we are discussing about whether it's normally distributed or not is because we are actually looking at the error distribution. If the reason why we are looking at error distribution normal or not is if it is normally distributed, then our our linear regression model, what we initially built, is accurate. So to come
Yes.
to that conclusion,
Yes.
we are doing this. Is that correct?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes. Yes, and you know, yeah. Yes, that's it. I don't want to confuse you more. Yes, that's it. That is good. That's what the thing is. All these actually talk about the same thing. I was actually about to talk about this and I stopped by again. And all are talking about this only. When data is linearly related, you will not have heteroskedasticity. You will have normally distributed error term. They wrote the same thing in different ways. But why we are discussing, we are trying to induce new concepts like QQ plot and the normal distributions importance and all that. Got it?
Sure, sir.
Okay, one more thing is that Shapier-Wilk test. We'll look into Shapier-Wilk test in SciPy, and I'll show you that the p-value and the null hypothesis and all that. Right, if you look at this Shapier-Wilk test, the null hypothesis that the data was drawn from normal distribution. Right, the null hypothesis is that the data is from normal distribution. When you do have the Shapier-Wilk test, you pass your X and do Shapier-Wilk test, you will get a p-value. Okay, the p-static p-value. So if the p-value is greater than 0.05, is the data normally distributed or not? Try to show this here. Did I do this somewhere? No, I think. Let me try to run this here and show you. So let me execute all above. Oh, some error somewhere. Numerical test time, graphically, visually, we try to see whether data is normally distributed or not. See this, the p-value is actually 0.02. Okay, and the statistic is 0.99. This is actually the t-score or z-score. Okay, what is this saying? When the p-value is less than 0.05, what we should be doing?
Rejected null hypothesis.
Rejecting null hypothesis. What is null hypothesis? Data is drawn from normally distributed data. The test is saying that the data is not normally distributed. Do you agree?
Yes, sir.
Right. So numerical also you can do, but when you look at this QQ plot, right, it will actually give you more clarity. When the sample size is small, your statistical values are not reliable. When sample size is big, right, you will definitely get a good p-value. Okay, only 32 records are there. It is unable to take many samples from it, and it would have done some virtuous thing there, and now it's showing like that. So the data is normally distributed there. Okay, the error term. So that's
in this case, we the test is not reliable. We should be relying on the QQ plot kind of stuff. Or
yeah. When data is less, right, plots are better. When data is huge, you should go with the tests here. These numerical tests.
okay.
Okay. So I think, you know, that's whatever theory we covered is going to help you understand these. If you don't know what is p-value, what is null hypothesis, what is hypothesis testing, you will not have any clue what this guy is talking about, right? So, okay, so that's another point we need to understand. Okay, so serial correlation. So data may have serial correlation. What is serial correlation? No, generally I take stock market price, right? Day one. I think we can relate this to our Giri's example also. Day one. Day one. No, some price maybe $10. Day two, $11. Day three, $12. Day four, no, $13. Day five, maybe $15. Day six, $16. Day seven, no, $17, like that. Okay, this is the data. Now I built a linear regression model. Now this is X and this is Y. Suppose that I built a linear regression model and then I predicted Y cap. So for first day it predicted 9, second day 10, 11, so third day 11, fourth day 12. I am taking a hypothetical example here. It's not going to be like this in real time. Okay, now if you look at the error, error Y minus Y cap. So if you look at the difference, right, it is 1, 1, 1, 1, 1. Right? So the error is like that, right? So if you look at serial correlation means, let me try to put it as, this one as ED1. What is serial correlation? I am trying to explain. Okay, ED1, ED2, ED3, ED4, ED5, ED6, ED7. Okay, so I named each of the error as ED1, ED2, like that. Okay, so here we are saying serial correlation. If you look at the statement here, it will be a bit confusing. That's where I tried to draw all that. Potentially very serious in time series regression model, right? Very, I don't know, potentially very serious in time series regression model. I think I need to change the statement. This problem is related to time series problem, right? The correlation between corresponding error terms separated by some other number of period is known as serial correlation. Do you understand anything by looking at the statement? The correlation between consecutive errors or errors separated by some other number of periods is known as a serial correlation. Let me explain that. When I say correlation, are we talking about one column or two columns? When we say correlation, are we talking about one column or two columns?
Two columns.
Two columns, right? But we have only one column here. The error term, only one column. So what this guy is saying is correlation between consecutive error terms. Consecutive error terms means what? ED1 and ED2, right? ED2, ED3, right? ED3, ED4, ED4, ED5, like that. So when you calculate correlation between this column and this column, if you have correlation, that means serial correlation is there in the error term. Got it? Got it?
Sir, can you please say what is ED1 once again?
I gave a letter, a character, a variable name to each of the errors here.
Okay. Okay.
Okay. So now this data will look like this: 1 1 1 1 1. I should have created a better data set there. Right? It look like that. So when you try to calculate correlation rate, you'll get one correlation because same value, right? Increasing or decreasing same value, right? So this is called a serial correlation. This is consecutive error terms, whatever I showed you, but you can take a, take a number of periods. Number of periods means between first error and the fourth error, second error and the fifth error, third error and the sixth error. Then what will happen? ED1, your data, your new correlation test, the serial correlation test data will look like this: ED1 and ED4, ED2 and ED5, ED3, ED6, like that it's going to be. Right? Consecutive or range, there is a gap, there is a gap between the. So either way, if you have correlation between the error terms, you say serial correlation is there in the data. Okay, serial correlation will happen maybe because of violation of linearity in the linearity, or the data set may belong to a time series problem and you are trying to build a linear regression algorithm. Right? The data set, is it belong to linear regression or time series, or general machine learning or time series, can be understood by fitting a linear regression algorithm and trying to look at whether serial correlation is there or not. Got it? Got it? Any questions? So Durbin-Watson test is a test which actually, when you build this OLS algorithm, it actually gives you the result. Durbin-Watson test. Our value is 1.65, right? So if you look at the Durbin-Watson test results, in the range, if it is Durbin-Watson test is equal to 2, no autocorrelation, less than positive autocorrelation is there, greater than or 2 to 4, it is negative autocorrelation. Okay. So also you can see residuals as time plot and look for serial or autocorrelation. That's it. So serial correlation can be avoided by adding interaction terms. We were talking about interaction terms, right? If you ignore interaction terms also, the serial correlation may happen. Okay, so try to induce interaction terms and see serial correlation is avoided or not. If still not avoided, that means the problem belongs to time series. Okay, and then the next concept is multicollinearity. Correlation, right? Correlation between two columns. But if there is a correlation between more than two columns in the input data, then you call it as multicollinearity. What is expected? Between input variable and output variable, you should have correlation, right? Do you agree? Between input variable and the output variable, there should be correlation. That we agree, right? Guys, between input variable and output variable, there should be correlation. That part you agree, right?
Yes, sir.
Yes.
If there is correlation within input variables, right? There may be a correlation between the output variable and input variable. We don't know, but within input variables, if there is correlation, right? And that too between more than two input variables, we call it as multicollinearity. Multicollinearity basically will not harm anything in your prediction, right? The model's predictive power, it will not harm. But feature selection, it is a problem. If 10 features are strongly correlated and they are all important in predicting target variable, which feature is important you cannot decide. Okay, to solve this problem, right, we'll use regularization technique where you will understand which feature is most important and keep that only, because when you are building a model, especially with thousands of features, you don't want to use all features there. If you reduce number of columns, right, your the processing power will reduce, or the need for processing power will reduce, and model retraining activity will become faster. So multicollinearity prediction perspective, there is no problem. Only performance and the model execution time perspective or feature selection perspective, it's a problem. Got it? Multicollinearity really is not a problem. But time dimensionality reduction perspective, it is useful to see whether multicollinearity is there or not. You can do the correlation plot, right? If you see too many red things, right, between these input variables, you can say there is multicollinearity in the data. So these are the linear regression assumptions. And any questions? I'll actually show the Giri's, we'll look into Giri's dataset also for maybe 5 minutes. If time is not sufficient, right, we'll see tomorrow, right? So